Welcome back to the third session of the second day of our short course on hypersonics, basics and applied. We previously talked about some applications of the hypersonic flow solutions that we looked at first day. We've looked at hypersonic boundary layer theory. We've looked at boundary layer profiles. We've talked about what happens if the engine swallows those profiles. We talked a little bit about the thermodynamics of the combustion system. In the last portion of my presentation, we'll be talking about some key problems associated with the design, some specific design issues, primarily focusing on the vehicle forebody and its interaction with the shock. I understand we have a question from a remote site. So why don't we, before we get into it, let's take the question from the remote site.
Hi, I just wanted to ask, you've mentioned several different types of engine configurations today, and I probably should have asked this earlier, but could you say a word about the superejector ramjet? It's something I did some reading about several years ago, and I was wondering what the difference was between that and a conventional ramjet and the other configurations.
Okay, well actually, let me give you a more generic answer, and that is that in the realm of hybrid engine concepts, there are really a nearly infinite number of schemes by which you can incorporate ramjet operation and compressor turbine operation. Several schemes that you're alluding to try to match a ramjet with rocket performance. So for instance, you might consider a ramjet which at some point in its flight can transition to pure rocket power. One scheme to do that, you might just have fuel inlets that at some point in the flight begin to dump fuel into the back region of the ramjet. The ramjet inlet might close off, and you run as a rocket all the way up. Variety of other engine concepts which incorporate that. I mentioned the hybrid concepts. I mentioned the air turbo ramjet. Other concepts in which dissipated heat is taken off the surface of the vehicle or taken out of the skin of the engine and used in some way to power a turbine have been investigated. But usually they involve incorporation of the generic engine types, rocket plus ramjet, gas turbine plus ramjet, using the afterburner of a gas turbine as if it were a ramjet, and then ultimately perhaps even using the afterburner of a gas turbine as if it were a generic rocket engine. Unfortunately, I don't have a view graph which illustrates the various types of engines, but there is in fact a fair amount of work that's actively being pursued, unfortunately mostly in Japan, on dual engine cycles, multiple engine cycles. And I don't know, Kevin, were you planning on talking at all about those?
Not in great depth.
Oh well. Another question that I wanted to answer in the break, someone came up and asked me about stability theory and its relationship to what we saw about the delay of transition at higher Mach numbers. And I wanted to point out that I think you can apply the exact same argument to stability for mixing in a stream of fuel in a supersonic engine, also to why there's the delay of transition at higher Mach numbers. Right? You know that from boundary layer theory, one of the theories that's been developed in boundary layer theory is to look at the way disturbances propagate in a laminar boundary layer. Tolman-Schlichting theory looks at the propagation, the stability of wave-like disturbances. And I think you can apply a similar argument that as you go to higher Mach numbers, wave-like disturbances in the boundary layer are less unstable. And that, to me, gives you a good physical feel for why boundary layers tend to be more likely to remain laminar at the higher Mach numbers. So it's really the same phenomenon that we see with the fuel mixing. And I thank the individual who brought that to my attention. In the few minutes remaining in this portion of the course, I just wanted to key in on this picture. And this is a picture which represents the vehicle forebody of a hypersonic vehicle, a representative engine cowl, and the bow shock that would be coming off the front of the vehicle. Now, actually, this picture is really upside down. This would be the undersurface of our hypersonic vehicle. But let's consider a couple of problems associated with this flow field. I mentioned that we want the bow shock to be somewhere near the cowl. It's not exactly clear how near the cowl, but we want to be somewhere near the cowl. Well, bear in mind there's this boundary layer. And the boundary layer thickness is a function of angle of attack. So first off, we might wonder what happens when we move the vehicle. If the vehicle shakes or if we approach a new angle of attack, boundary layer thickness is going to change. The effective height, effective thickness of the vehicle is going to change, and therefore the bow shock is going to move. There might be other effects. The vehicle might be bouncing around as it's flying. Are we going to be able to match the bow shock if the vehicle is bouncing? Does the shock stick with the vehicle, or does it bounce at a different rate or with different amplitude relative to the engine cowl and so change its relative position? That's a very interesting question. And the answer is not immediately obvious. Right. First, reasons for wanting to match the shock to the cowl. You want to minimize drag in all these hypersonic configurations. You want to avoid swallowing the shock, because if you do, it will reflect on the engine and probably induce deleterious effects. You want to avoid spillage. That means you want the shock to be pretty close. You don't want it to be far below the engine. But at the same time, you probably don't want the shock to be exactly touching the lip for reasons that we'll see in a few moments. So that's probably pretty tight criteria. Now let's look at a very familiar diagram, the theta beta M diagram. This is a diagram that shows shock wave angle versus deflection angle. And one of the questions we can ask is, if I go through a different deflection, let's say, for instance, I have some surface, and let me go to another. Let's see if it's possible to get these both on the same view. Ah, yes. If I have a surface with an inclination of angle theta, and it's producing a shock wave at angle beta, one of the questions I can ask is, what happens when I change that angle theta? Does the angle beta change by the same amount as my angle theta? And if it does, my engine doesn't notice the fact that my angle of attack has changed. All right? If I have an engine sitting here, and if I increase angle theta, but beta moves by the same amount, then the engine still sees the shock attached to its lip or near its lip. On the other hand, if I move theta, but beta doesn't change by as much, or if beta changes by more than theta does, then the relative position of that shock will change on the cowl. And that becomes a design issue we'd have to worry about. Looking at the theta beta M diagram, you can see that in order for me to assume the conditions that the shock moves with the surface, I would have to have a slope of 45 degrees. And even though these aren't plotted to the same scale, you can see that the lines which give beta as a function of theta are curved. They're not straight lines. And in general, there are only single points on these. There's a single point at each Mach number at which I can realize the condition of changes in deflection angle producing identical changes in the shock angle. In other words, in general, when I change the angle of attack of the vehicle, the position of the shock is going to change relative to the cowl of the engine. And that's another design consideration I have to worry about. If I actually look, I can derive the equations which describe that, just going to the familiar shock solutions. In the shock solutions, we can describe the relative angle between the shock, beta, and the surface, theta. And here I've added in an alpha which represents an angle of attack. As far as the shock is concerned, the angle of attack of the surface and the theta, the actual inclination of the surface, add together, because the flow only sees the effective inclination, which is the sum of these two. I can do that. I can solve for the relative displacement angle and seek a solution in which that relative displacement angle is insensitive to changes in the angle of the shock or the angle of the surface. When I do that, I can actually plot out and find that I have one fixed angle, one fixed surface angle at any Mach number that gives me that condition. What does that say? Well, if I have a vehicle that's flying through a range of Mach numbers, I have no hope of being able to match the shock to the cowl if I have varying flight conditions. Right? Angle of attack is going to change those conditions, and the engine must be designed to accommodate that. Similarly, if I change flight Mach number, this is a plot of shock displacement off a 30-meter surface. And all I'm showing this, the reason I'm showing this to you is to indicate that as Mach number increases, the shock displacement increases as well. In other words, if I design an inlet with a given geometry with a bow shock, as the Mach number is increasing, the position of the bow shock is changing relative to the surface and relative to the cowl. For now, the suspicion is that something like NAS would have to be designed to accommodate that changing shock position. Whereas you might actually design it so that at lower Mach numbers, the shock is sitting far below the cowl. And then as you increase the Mach number, the shock moves up towards the cowl. And then eventually you get some crossover point and the shock gets swallowed into the cowl. Similarly, I think I can skip through this one. Similarly, we can ask, we saw that it was important to provide appropriate thermodynamic conditions inside that engine. We want to provide appropriate temperature, and we want to provide appropriate pressure. Once again, if the shock is changing, those conditions will be changing as well. And it's very difficult to fix those conditions. That means we have to have some flexibility in the design of the engine. If we try to seek solutions that give us fixed thermodynamic properties, we can do it analytically, and we find out that we wind up with impractical solutions. So real inlets have to have some degree of flexibility. And that's a measure of the, I think it's a good measure of the performance of the inlet. Okay. I'm going to be skipping some of the notes because I promised Dr. Bocat that I would not eat into his time. And he's threatened me that I will be dealt with bodily harm if I do. So let's just talk about what the effect of a boundary layer will be in that whole process. Remember, the boundary layer scales with the inverse square root of the pressure ratio across the shock. Increase the surface angle, you get a stronger shock, higher pressure ratio, thinner boundary layer. Well, the boundary layer represents a substantial portion of the flow going into the engine, and that also is going to change dramatically the flow that goes into the engine, and also the position of the shock over the surface and the position of the shock relative to the cowl. That's another thing that must be considered. Now, what about if the vehicle is oscillating? What if it's shaking? Then what hope do we have of being able to match the bow shock to the lip? That's also a difficult problem to solve. There are really two limits. One is a limit that's indicated here. It's a quasi-steady limit. In other words, consider what happens when the vehicle shakes, but assume that the time scales are such that we can treat the flow over the surface of the vehicle at any point to be a quasi-steady flow. And we can do those solutions, and you'll see in your notes there are the quasi-steady analogs to the full time-dependent continuity equations, full time-dependent energy equation, and full time-dependent momentum equation, and you're free to go through those at your leisure. And one of the conclusions we draw is that in the quasi-steady limit, it turns out by and large, when the vehicle shakes, the shock moves with it. That's rather reassuring. There's another limit we consider. That's a very, very high frequency limit. The quasi-steady limit won't apply to the high frequency limit. However, at extremely high frequencies, think about what's happening. The vehicle is shaking. The surface is shaking. Once again, I'll use the pointer to indicate the surface of the vehicle. Or in fact, maybe even better. Let's go back to my initial cartoon. Okay. If that's the surface of the vehicle is shaking. If it's shaking very rapidly, it's giving off compression waves and expansion waves. Well, at very high frequencies, the compression and expansion waves will cancel each other out before they ever hit the bow shock. So in the very, very high frequency range, say if this thing is shaking in the kilohertz range, the bow shock will be unaffected by vehicle motions. The important range is going to be the mid-frequency range, say in the 10 to 100 hertz range. That's where we're going to expect some oscillations, perhaps from engine-induced oscillations. That can't be approached from either the quasi-steady solution or either the high-frequency solution. And one of the conclusions that we draw there, we've done some computational modeling, and we found that indeed we can see some dramatic motions of the shock, whip-like motions of the shock in those frequency ranges. And that's also something that must be considered. Shock on cowl will be very difficult to accomplish in a steady state, with a steady state scenario. Okay, I have been alluding to another problem associated with the shock on cowl, and that is a fascinating interaction. It's called a shock-shock interaction. The problem was first investigated extensively by a gentleman named Edney. And what Edney discovered was that if he had two shock waves, such as the shock wave associated with the bow of a hypersonic vehicle, and the shock wave associated with the blunt leading edge of a cylinder, or in our case, the blunt leading edge of the cowl lip, the interaction of these two shock waves produced a very, very complicated flow field, and a flow field which could have ominous implications in the design of the vehicle. Specifically, Edney discovered, and it's since been confirmed by many other people, including Holden, a gentleman at NASA Langley by the name of Al Wheating. It's been shown that this bow shock interacts with the blunt body shock in such a way as to produce, under certain conditions, a free jet. And that free jet impinges on the surface and produces very, very intense local heating. Essentially, it's a blowtorch aimed right at the surface. And you can imagine if this is the cowl of the engine, if you have that blowtorch pointed at that cowl, the cowl is not going to survive very long. This was demonstrated quite dramatically back at the end of the X-15 program. They did a flight test with a dummy hypersonic engine, and they had it mounted on a pylon underneath the vehicle. And they discovered when they got the vehicle down to the ground that the pylon, was a titanium pylon, had melted off. And the best reason that's been suggested for why it melted off was a shock-shock interaction producing a free jet that burned right through the pylon. And by the way, it also did some fuselage damage, which made the pilot very unhappy when he saw it. Just looking, there are a variety of shock interference patterns. Generally, they're indicated by the location that the impinging shock hits the blunt body. There's a type 1, a type 2, a type 3, type 4, type 5, and type 6. And in your notes, you'll see cartoons which represent what each one of those interactions looks like. And I won't bore you with the details of any of those interactions. You can peruse them at your leisure, except for the type 4 interaction, because that's the one that poses the most danger to an engine cowl. That's the one that has the free jet pointing right at the surface. And it's interesting because we can see exactly why that free jet occurs. If you look at the next page in your notes, I hope it's the next page in your notes, this is a representation of the flow field that is associated with this shock-shock interaction. This line is the cowl bow shock. This line is also the cowl bow shock. This line is the inlet shock. Now look at what happens. Inlet shock strikes the cowl bow shock, and it generates this intermediate shock, which is a transmitted shock. And this shock is of sufficient strength and at the right angle to match pressure and velocity directions. Associated with this is also a shear layer. And then on this side of the transmitted shock, the bow shock continues. Well, think about what happens to flow passing through this flow field. The flow that passes across the cowl bow shock sees a relatively strong shock. Also down here, the flow that passes through the bow shock sees a relatively strong shock. But look at what happens to the flow that passes through here. First, it goes across the inlet shock, and that's a relatively weak shock. It's a relatively oblique shock. So it doesn't see much of a total pressure change. In other words, it has most of its kinetic energy. Now it passes through this second shock. This transmitted shock also generally is a weak shock. So again, it sees very little total pressure loss, very little loss in kinetic energy. Well, now this flow that has passed across the transmitted shock is in this region between two shear layers. That flow has almost all of its kinetic energy, whereas the flow on either side of it has lost a lot of its kinetic energy because it's passed through strong shocks. In other words, this is like a blowtorch pointing, and if the surface is sitting here, it's pointing right at the surface and could melt through the surface. And there have been extensive measurements done. As I said, Holden has done a lot of measurements in which they show that the heating associated with the region where this supersonic jet impinges on the surface can be 30 times greater than the heating on either side of that jet. Okay, let me show you some data. This is data which comes to us courtesy of Al Wheating and Mike Holden from the AAA Journal. And this shows fairly dramatically. This is, let me call your attention to Figure 4. The square boxes on Figure 4 show the Type 4 interaction, and the round circles are undisturbed. Notice that in this data, the undisturbed circles, the heat transfer is way down here. Look at what happens at the point of impingement of that free jet. The heating rates have gone up, in this case, almost 20 times. And that might spell disaster for that cowl lip. So one of the goals in dealing with the shock on cowl problem is to try to make sure that the shock does not exactly touch the cowl, and to minimize the time. If that shock sweeps by the cowl, you really want to minimize the time during which that shock passes by the cowl. And here, let me show you some Schlerin pictures, again, courtesy from Mike Holden. And you can actually see, let me call your attention, this is a Type 4 interaction. You can actually see the picture. This is a free jet impinging I think this was a sphere in the cowl span tunnel. And it's quite a dramatic effect. Okay, one of the ominous aspects of that interaction, by the way, is it seems to be unsteady. Wind tunnel measurements have shown that it bounces around. There's been some computational work that also shows that it bounces around. So you can imagine, not only do you have this free jet pointed at your cowl, but it's a free jet that you don't even know where it will be located on your cowl. So it's also a design condition. And even if you design your bow shock system so that that jet isn't pointed at your cowl, because it's unsteady, you might very likely have a situation when a free jet appears when you don't expect it. And that's another advertisement for a research area that deserves more investigation. Okay. I won't go into too much about the last two view graphs. They suggest some sources of that unsteadiness. Right now, we don't really know what causes that unsteadiness. And I think it's important that we find out before we can properly account for the effect of shock impingements on a cowl. OK, one last issue that I want to talk about before I turn the podium over to Dr. Bocott. And that is the problem of an unstart. Now, for those of you who are familiar with conventional aircraft engines, you know that one of the issues we deal with is something called an unstart. And that is the disgorging or the formation of a strong, usually normal shock in front of an engine when one was not expected. Let's say, for instance, I design a fighter aircraft. I design it with a ramp inlet. I'm expecting weak oblique shocks. And then I'm flying along, and all of a sudden I do something that causes a strong normal shock to form at the front of the inlet of my fighter aircraft. What is that going to do? Well, one, it's going to change the conditions going to the engine. Thermodynamic conditions are going to change. More importantly, a normal shock has a higher total pressure loss associated with it than an oblique shock. So for a low-speed engine, for a Mach 2 engine, an unstart is going to ruin my engine performance. Well, now let's think about what it will do at high speeds. Let's think about what it will do if we're flying hypersonically. Right? In the hypersonic limit, the total pressure ratio across the engine scales inversely with the fifth power of Mach number at gamma 1.4. So it is extremely sensitive to Mach number. Think about what happens then if we go from a weak oblique shock and suddenly form a normal shock. Think about what's going to happen to the total pressure inside the engine. It's going to drop way down, and the engine performance will become nil. Situation can become even worse, though, because total pressure isn't the only part of the story. Let me just indicate, you can see that effect if you look at we talked about kinetic energy efficiency at the beginning of today. Just look at how kinetic energy efficiency scales under the influence of an unstart. If we suddenly form a normal hypersonic shock, the kinetic energy efficiency is approximately proportional to Mach number to the 1.4 power minus 5 divided by Mach number squared. This can generally become a small number. Typically, flight at Mach 10, we might design the inlet with a kinetic energy efficiency of about 97%. An unstart could drop us down to 80% or lower, 70% if we're not careful. But as I said, efficiency isn't the only part of the problem. We can skip over the next view graph and go to the view graph labeled unstart static pressure. Right? Think about what happens to the static pressure inside this engine. The pressure ratio, the static pressure ratio across a normal shock is very much greater than the static pressure ratio across a weak oblique shock, especially at the high Mach number end. All right? From the tangent wedge model, we can get an approximation for the pressure ratio across a shock at small angle. And here you see the hypersonic similarity parameter, Mach number times the angle of inclination. Let's compare that to the pressure ratio across a normal shock. Right? We can solve for the original design value, the tangent wedge oblique shock value, by some specified design pressure ratio. And then compare the pressure with an unstart to the pressure that we expected in the original design value. And the next view graph shows you a table of some of those numbers. Right? As a typical example, hypersonic flight, flying at 30 kilometers, pressure ratio is 20 across the shock system. That gives a design inlet pressure of about 1/4 of an atmosphere, which would be fine for hypersonic combustion. look at what happens. At Mach 5, we have an unstart. The pressure with the unstart is 1.5 times the pressure design. Well, not too bad. Look at what happens when we go to Mach 20. The static pressure with an unstart is almost 25 times greater than the static pressure we designed for. At Mach 25, it's almost 37 times greater. Well, think about what that's going to do to the engine. It could easily blow the engine apart. It could be loss of engine, loss of vehicle. So we're talking about more than losses of performance. We're talking about loss of pilot. And that's another critical issue that remains to be addressed. And this is another advertisement for a critical research area in hypersonic propulsion. And with that, if there are no questions, I think I've almost made it to my time limit. So I'll turn the podium over to Dr. Bocat.
Thank you, Mark. Let's see, I'm going to do this a little different. I think I'll slide this, well, I'll leave it there for now. Clean it up a break. I'm going to try this sitting down. I've got a lot of material to cover. I'm going to build on what Dr. Lewis has started. I'm going to basically bury you with material, and it's going to make it hard to get it all done in time. I've got it blocked into 15-minute blocks, and as I approach my 15-minute limit for each, I'll sort of pass over what I didn't cover in that area. I'll briefly glance over it. But I've given you enough material that I think you can study all the issues associated with hypersonic design, specifically a single-stage to orbit design. I really want to address all the design requirements and all the physical issues, and Mark has already touched on a number of those. So it'll be quite fast-paced. There are a number of charts that were not in the package sent because of time constraints. I've got projected here, if you could show down Ann Hawker, who you've probably heard her name, is in charge of this program with the IAA, and her phone number. If you call her, if you're interested in getting the remaining charts, she'll get you a copy of those. I want to give some special thanks. I had a lot of people give me a hand supplying me with some information for this. At NASA Langley, Zane Pinckney was particularly gracious. He ran a lot of nose-to-tail solutions, and we'll see those later, the flow path to get an idea of the performance of our design. Greg Gatlin, Carl Trexler, Chuck McClinton. At NASA Lewis, James Walton. Pratt & Whitney, Jim Kinsey. Tom Powell, Don Stewart. And at Rockwell, Marty Bradley, Deloy Olson, Bob Johnson, Art Grants, and Dick Cervisi really helped me out quite a bit. I'll start off with a little different picture. If you could show down, I hope this shows up. It's not real clear, it is a view graph, but you can see a little bit. This is an artist's conception of the NASA team design, and it's quite a bit different than earlier pictures you've seen. I'm going to cover, I'd like to just introduce you to the agenda here, items I'm going to cover. First of all, accelerators versus cruisers. Touch on that very briefly. I'm going to concentrate on the accelerators. Didn't have enough time to really get into both areas. Requirements for single-stage orbit, cover our baseline design. What we're going to actually do here is have some fun and go through a design, not an elegant design, not an optimized design, but we're going to design a plane. I thought that might be a good way to introduce you to the issues of a hypersonic design. Cycle selection, preliminary sizing, takeoff considerations, wing and control surface sizing, transonic considerations, hypersonic, finally trajectory and sizing, all important issues in hypersonic design. Hypersonic design tends to be a very coupled, interactive, multidisciplinary activity. Changing requirements of aircraft with Mach number and mission. At lower Mach numbers, still supersonic, engines tend to be independent of the airframe, and as you go to higher Mach numbers, the engine needs to be more and more integrated because more and more area is required for capturing air and providing thrust, and more area is required to supply thrust to act as a nozzle. These numbers you see up here are so-called ram drag and gross thrust. Ram drag being the drag on the forebody, which is the actual forces plus the momentum term. You can see that they get very large at higher Mach numbers. A lot of confusion resides with those numbers. They are not real forces. They're not forces that actually act on the plane. If the engine were to go out, you wouldn't have 2 million pounds of drag on the plane at Mach 12. Most of that's flow momentum, and it doesn't act on any surface. It's an important point I just wanted to make. Typically, hypersonic cruise vehicles require high lift-to-drag ratios. Wave riders have been mentioned for that. Hypersonic accelerators, on the other hand, require low drag and high forebody compression efficiency, and a number of other things we'll talk about here shortly. Some single-stage orbit requirements. Takeoff is a very important requirement, and it's a tricky one to have a good hypersonic shape that also takes off. Adequate thrust margin at all Mach numbers. Transonic tends to be a problem, and extreme hypersonic Mach numbers are also. The plane must be stable and controllable. It's not a plane if it's not at all Mach numbers. Adequate thermal protection, stable inlet operation and combustion, adequate L over D primarily on entry for cross range and landing. Rocket will always be required. You don't have, you can get to orbital kinetic energies in the atmosphere, but you're not at an orbital altitude, and so you have to get your final delta V from a rocket, and then you have to protect your engine on entry. What about fuel selection? Dr. Lewis touched on this. I'll just make a couple additional points. Hydrogen is more energetic per unit mass than other fuels. It has the highest cooling capacity of any known fuel. Very rapid reaction kinetics, and Dr. Lewis described why that's important. However, it is also less dense, takes more volume, which means drag. This just gives you an idea of what the density of JP4, which is a typical turbojet fuel, versus liquid hydrogen, and then the heats of combustion, the amount of energy you get out of each. Shown down here are ISPs of different fuels, and it's just showing you the theoretical limit. ISP, specific impulse, was already defined by Dr. Lewis, and it shows how much higher hydrogen can be theoretically. And then over here was some work that actually Jones and Donaldson did. It appeared in Aerospace America a few years back, showing what the mass fraction being the mass of fuel over the total mass of the vehicle, is required to get to an orbital velocity of 26,000 feet per second. As you can see, for typical fuels of the past, like X-15 fuels, you could never make it to orbit. Even with hydrogen oxygen, it'd be very difficult, though in the latest issue of Aerospace America, there are articles on single-staged orbit with rocket propulsion. So there, theoretically, it does appear to be possible, but you're right on the limit. JP fuels, theoretically possible, though thermodynamically, kinetically, it's not. And hydrogen's really the only viable option. So that's what we're going to use here in our design. Slush hydrogen is another item. Slush hydrogen is a mixture of solid and liquid hydrogen, which helps densify it. We're not including it in the design, but it is something that can be considered for a hypersonic design. Okay, forebody requirements. High compression efficiency, low drag and high mass capture. This parameter mass flow per unit drag I'll talk about more later. It's a sort of an interesting parameter to look at. Flow uniformity, Dr. Lewis talked a lot about that. Cross flow is an issue for transition and uniformity. Uniformity is very important if you want all your engines operating the same, and that's an uncertainty that you probably wouldn't want to deal with. So uniformity is quite important. Uniform boundary layer transition, good volumetric efficiency. That low density hydrogen's got to be packaged, and that's tricky. Design options, a lot of them, cones, wedges, spatula shapes. I'll describe all these, bi-elliptic cross sections, combinations, and wave riders were mentioned. I originally didn't include it. Wave riders are good L over D devices, and so for that reason you wouldn't necessarily apply them to an SSTO, but the flow uniformity may make it a viable option. This was a little analytical study I did quite a while ago. Wedges versus cones. Is there some inherent performance benefit of one over the other? So I looked at basic two different flying engines here. You know, a wedge flying engine and a cone. There's nothing but propulsion system here. Four bodies are part of the inlet, and the aft part's part of the nozzle. I can't go through all the assumptions, but I use this thrust equation here, if you could focus down in the lower right-hand corner. This is a small disturbance approximation for net thrust in the engine. It is based on perfect gas, and that was used to evaluate these, including viscous effects. Here's some of the results. Effective specific impulse. This was done at Mach 20 at a free stream dynamic pressure of 1,500 pounds per square foot, forebody length of 125 feet. These R's are total pressure recoveries in the inlet combustor nozzle. 1%. You do lose a lot of total pressure, as Dr. Lewis pointed out. Propulsive efficiency of 0.6, which is probably high. You'll see that in a little bit. And ratio specific heats of 1.3. For cone angles, this down here, you'll see the cone angle and the wedge angle at the bottom. I've plotted these in terms of equivalent cones and wedges. I define equivalence as having the same losses across them, and it turns out they have the same contraction ratio, or contracting of the area ratio of the flow, and this is the correspondence shown down here. For equivalent cones and wedges, you don't really see much of a difference in performance. At very low angles, perhaps cones would be a little bit higher performance. It's a study conducted at NASA Langley a number of years ago, looking at forebody shapes and how to shape the forebody to deliver uniform flow to the inlet. These would probably be classified as bielliptic shapes, and that's an interesting study. Everything I show here I do reference. I have 55 references at the end, and it gives you an opportunity to delve into any of this stuff in more depth. Spatular shapes are an interesting design option. This was an idea first developed by Jack Pike in Britain. They are shapes that minimize drag, and as it turns out, here's a line of drag of a spatular shape versus cones at equivalent base shapes. And the spatular shapes do produce quite a bit lower drag. And so they do provide us with an interesting design option for a hypersonic aircraft. Down below, I show basically a forebody trade study conducted by Wilson and Davis, where bielliptic shapes were used to try to optimize the compression efficiency of forebodies. And this is an area that's very interesting to look at and very useful. That compression efficiency is important to the design. Another aspect I mentioned was volumetric efficiency required for packaging that fuel. Here you see a plot courtesy of Dixer VC at Rockwell International of wetted area as a function of length of the vehicle. And look at any length, it doesn't really matter. What you see is a progression of wetted area that increases as these shapes change here, and that's volumetric efficiency. The more wetted area, the less volumetric efficiency. More wetted area means more weight, more skin friction drag, etc. Down at the bottom, the highest volumetric efficiency is in round shapes. Think, cones. Round shapes tend to be more volumetric efficient. And as you go to square and square shapes, it does become less volumetrically efficient. Okay, here's our design. This is what we're going to be working with today in terms of analyzing it, looking at all the issues. It's not particularly elegant or anything. It's just something that I started with as a baseline. Very simple, very rough, very round numbers. 1,000 inches long. Place the inlet such that I wanted to have a contraction ratio of 40 as the baseline starting point. It's about in the right range for hypersonic conditions. So at very high speeds, contraction ratio of 40 is probably a reasonable place to start. So with that starting point, and recognizing how important it is to mix fuel and air together and how difficult it is to mix fuel and air together, I kept the throat height at 2 inches. And those two design considerations basically place the cow lip location at 600 inches aft of our nose. It's got a 3-ramp inlet with a flat cowl, a constant area combustor. We'll get into some of the details of this later. Things like the wing size and elevon size are established for stability and control reasons, And we'll get into all those details later. So I just wanted to introduce, this is what our baseline plane looks like we're going to be studying here. This is artist concept. It goes with that color picture I showed of the NASP. And you could, if you remember what the last one looked like, it's not too dissimilar, this artist concept, from what I showed as a baseline. Okay, we'll start in with selecting propulsion systems. Dr. Lewis already showed this same basic plot showing the specific impulse or performance of the engine with Mach number. Turbojets are clear winners at low speeds, and then ramjets and scramjets at high speeds, all of which are better than rockets. You'll see later why specific impulse is important, how it factors into aircraft size. I derive that a little bit later. It's wrapped up in the rocket equation. Low-speed accelerator options have also been touched upon. Not going to really get into them too much. Turbojets, air turbo ramjets, turbo rockets, aerodynamic rockets. Most of these have been mentioned by Dr. Lewis. Fred Billig, Dr. Billig, gave a short course a few years ago where he talked a lot about these, and I can reference you to that short course if you want to learn more about the different low-speed cycles. Typically, the low-speed engine is sized. Its size and how much thrust is required is determined from the transonic pinch point. That's an area that's hard to get through because of the basic requirements of the aircraft at high speed dictate that the base is large, the nozzle is large, the inlet's large, creates a lot of transonic drag. And so the low-speed systems or engine tends to be sized for that transonic point. In this study, the choice of engine I selected was the turbojet, an advanced turbojet. Typically, the choice, though, is driven by cycle performance on the one hand, engine weight and volume. You don't use the low-speed engine for a very large portion of your flight, okay? Maybe up to Mach 2, 2.5, something like that. And then it's dead weight you're carrying to orbit. So thrust to weight is a very important driver. The volume it takes up is important. Any volume it takes, you can't have fuel there. Again, I mentioned picked advanced turbojets for this study. It's off the shelf, and the performance is well quantified. Down here I show how a typical integration of a turbojet with a scramjet, where you might mount it above the scramjet, have an auxiliary inlet forward of the main scramjet inlet, and then a nozzle that exhausts into the main nozzle of the scramjet nozzle, both of which would have to be closed off when that engine's not being used. Just very briefly, in the package you'll see some performance curves supplied courtesy of Pratt & Whitney for an advanced. It's not for any specific engine, but it's for like typical or modern day technology. Here's thrust to weight ratio versus Mach number for different altitudes. The remaining charts include nozzle pressure ratio, specific impulse. And then in terms of the size of the vehicle, the engines, I just sized them after the Pratt & Whitney F100 turbofan engine. That gives you an idea of its size and weight. So from the thrust to weight, you can determine the thrust. It also tells you how much mass flow is going through the engine. So those can be referenced for those kinds of calculations, and we'll use those a little bit later. Okay, what about the high-speed flow path? We've got the flow path below the ramjet, or below the turbojet, acting in one flight regime as a ramjet, in another flight regime as a scramjet. Now, that becomes a tricky design consideration. You can't, it's very difficult to have a fixed geometry operate efficiently across the Mach number range, even if it's just a ramjet and a scramjet and don't even have to worry about the low speed mode. Ramjets require, first of all, to start the inlet. Dr. Lewis talked about inlet unstarting. Eventually you have to start that inlet, swallow the bow shock that's out in front of the inlet, make it go inside the engine and eventually dissipate it out the back of the engine. When it's in the scramjet mode, you don't want that normal shock anymore. The only way to do that is to limit the contraction ratio across the inlet. It has to be small enough that the inlet will start. So you have to be able to open up the engine somehow. In the scramjet mode, you want high contraction ratios to increase the pressure in your engine, to decrease the Mach numbers, to reduce those losses of adding heat to a high Mach number flow. So it really does require some variability. You also need to have some divergence in the combustor to add heat, or you'll choke it out. So there's a number of ways to do it, and two options are called out here. One is to have variable geometry on the sidewalls. Tends to be mechanically complex and heavy, and it's a sealing challenge. Another would be to move the cowl up and down, which actually increases transonic drag and reduces your high-speed capture for the following reasons. If you look at the cowl, and if you have to pull it downward to open it up at low speeds, then you still have these very steep ramps out in front that are there for hypersonic reasons only. And those steep ramps, as we'll find out later, produce a lot of drag. If you could have collapsed the body side, you could have gotten rid of that drag. Also, at high speed, you've got to clamp the thing down to increase the contraction ratio, as shown down here. Well, if you move the cowl in that direction, you're capturing less air. The amount of air you capture is a function of how low the cowl is. So there you've got a performance issue, and here you've got a weight mechanical complexity issue. Okay, I showed you our baseline vehicle. Rough numbers, they were just wags how long the dimensions of that vehicle, 1,000 inches long. It's probably important to take a preliminary look at if you're in the right ballpark for the vehicle size. Are you in the range? The reason for that is if you're not and you have to later size the vehicle up, you'll find that you'll have a takeoff lift issue. The volume and weight of the vehicle scale as length cubed, so they scale faster than the planform area does. The planform area is where you get lift, so you're gaining weight faster than lift. So you want to get in the right ballpark. Now, I've included in the notes a set of notes that Bob Krieger from McDonnell Douglas generated and used in an AIAA short course a couple years ago. They're very valuable for looking at the geometric characteristics of different shapes and configurations and trying to get an idea of how much the plane might weigh. I took that baseline configuration and calculated the volume, planform area, and wetted area of that shape. I then went through his charts, his graphs and figures, and figured out all these other geometric design parameters and calculated the propellant fraction of our baseline vehicle. And it came out at a very low 0.38. And if you look at that chart I showed before, 0.38 will not get you to orbit. Okay? At best, we have maybe a hypersonic cruiser. Now, we'll point out a couple of numbers. I don't have a lot of time to go through all of Bob Krieger's charts, but I will point out just two of them. One is this, that the fuel density does impact the size and drag of the vehicle. As you go from sort of lower speed vehicles to very high speed vehicles, the volume has to increase due to the, first of all, fuel mass requirements to get you to those high speeds, and also because of the density of the fuel. And your drag will then go increase for those higher volumes and lower volumetric efficiencies. And similarly, your lift-to-drag ratios will go down. That's an interesting trait I just wanted to point out. In his notes, he also points out a couple sort of typical values for some of these geometric parameters, and you can spend some time perusing these notes and sort of getting a feel for these parameters. But I just wanted to point out that for our baseline vehicle, our value of kV was 0.47. Well, that's okay. That's about down in this hypersonic range here. Our value of KW is 2.29. Well, that's more like a fighter aircraft, very low. KP, if you refer back to the other sheet, was 6.22. That's also up in this regime. And KGO for our baseline vehicle was 75, which is maybe more down in this the regime of a hypersonic cruiser down here, or a lower Mach number hypersonic accelerator. So, like I pointed out, at best right now we've got a hypersonic cruise vehicle. So it does require right off the bat some scaling. Now, how do you do that? How do you scale? First of all, it's important to get an idea for the propellant fraction required to get you to orbit. Okay, I don't really have time to develop this, derive this, but from Newton's, right from Newton's second law, you can derive an approximate rocket equation, and the rocket equation tells you, given an ISP, will tell you how much fuel, what mass fraction, the mass of your fuel divided by the total mass of your vehicle is required. Jones and Donaldson made approximations to the ISP, or the propulsive efficiency, and the thrust-to-drag ratio that allowed you to get a closed form value for the mass fraction, shown here at the bottom of the chart. Propulsive efficiency, by the way, is the ratio of power delivered to the airframe over the power or energy in the fuel. And this is that chart I showed earlier, the graph of mass fraction as a function of velocity, just repeated for you to refresh your memory. For different propulsive efficiencies, what it requires in terms of mass fraction to get to orbit. And the lower plot shows the mass fraction requirement as a function of propulsion efficiency. The different lines are different propulsion efficiencies. And we'll see later that a value of 0.4, 0.5 is pretty reasonable. And then also a function of thrust-to-drag ratio. Thrust-to-drag ratio is an important quantity, but it's also a tricky one. It depends on where you define the dividing line between thrust and drag. And it's very arbitrary and somewhat nebulous, and we'll talk about that a little bit more later. Okay. Assuming a value that Donaldson and Jones assumed of thrust-to-drag of 3.5, and then also assuming a value of 0.4 in propulsive efficiency, and that's somewhat substantiated by this plot of Swithenbank that shows propulsive efficiency as a function of Mach number for turbojets, ramjets, scramjets, and rockets. And you can see that as you go up in Mach number and you change engine cycles, you do increase in propulsive efficiency to the point where maybe you get to about 50% maximum for a scramjet. So an average value of 0.4 is probably not bad and in the range of the upper limit. So using that value of 0.4 and a thrust-to-drag of 3.5, the heat of combustion of hydrogen, orbital velocity, and a reasonable orbital altitude requires a propellant fraction of 0.62, not that 0.38 that our vehicle is actually able to deliver to us. What are reasonable propellant fractions? What's historically reasonable? Rockets typically are high because oxygen is very dense. 68% for the old V2, German V2 rocket. Viking rocket, a more modern rocket, 80%. B-52, 68. Airplanes are lower. 747 is 32%. It'd only be 33% if you filled it all with liquid hydrogen. The Voyager, which probably has the highest one in the world, 79%, would only be 28% with liquid hydrogen. That's a real challenge to get that into a vehicle. And I think we're about the point where we've got to cut off, and we'll pick this up as soon as we get back. But this will just describe how we use that propellant fraction to scale up our vehicle and get a more reasonable size. Are we at our breaking point? Okay, we'll go ahead and break there and I guess come back in a half an hour?
Oh, yeah.
Half an hour, okay.